illustrious speaker tonight.
Hi, I'm Al Estes, head of the Architectural Engineering Department. Love playing before a standing room only crowd. It is my distinct pleasure this evening to introduce our Hearst speaker, Ed Saliklis. And this is a real treat. It's very rare that the Hearst lecture series gets a structural engineer, and even rarer that that structural engineer is an Archie faculty member. So we win on 2 counts here, which is why every seat is filled. Prior to coming to Paradise, Ed was pretty much an East Coast Midwesterner. He got his undergraduate degree from the University of Illinois, Chicago, his master's degree from Syracuse, his PhD at the University of Wisconsin-Madison, and then taught for 8 years at Lafayette College until he came out here to California. And since Ed arrived at Cal Poly in 2005, he has literally done everything. In fact, when I found out that I was going to get to introduce Ed, I struggled with what should I tell you about Ed. You know, I thought, should I tell you about his 2 patents? Should I tell you about his versatility as an instructor? He's probably one of the only people on the Archie faculty that can teach a first-year architecture studio in the morning and a graduate level engineering class in the afternoon and everything in between. Or should I tell you something about his research interests? He kind of has his hands in everything. He will incorporate students, write up the paper, and then go present the conference paper all over the world. Literally Poland, Germany, Portugal, Spain, Japan. I know because I have to pay the bills. Ed, probably more than any other faculty member, hits me up for money. But that's a good thing. A faculty member who's not asking for money is not doing anything. Or should I tell you all about the summer exchange program we have in, it's not an exchange program, it's a summer learning program in Lithuania. Yes, you might ask, well, why Lithuania? Well, it's because Ed organized it, and Ed is Lithuanian. In fact, Ed is my favorite Lithuanian. and not just because he's the only Lithuanian that I know, but or did I want to tell you about the fact that Ed has written a book? Many structural engineers sit around, drink beer, and say they're going to write a book, but very few translate beer talk into reality and actually write a book. And Ed has, and that's really going to be the subject of his talk today, so I shouldn't tell you about that. So what I really want to tell you about Ed is that Ed is the ultimate showman. He's brilliant on the stage. Those of you that have had his Archie 260 class know it. I know it personally. From an Exceed teaching workshop that I've been running probably been part of for the last 20 years. It's a week-long boot camp that teaches teachers how to teach. Most of the Archie faculty members have been there. And I do a seminar on stimulating positive emotion in the classroom. Things like drama and music and humor and compelling stories, something to make your education more exciting. And Ed is a big believer in that. In fact, when I give this seminar at the Exceed workshops, this is an actual slide. I put this marvelous picture of Ed up there. And I offer this quote because I think it really sums up how I feel about it as well. Ed says, "Every lesson aspires to be a finely tuned and well-orchestrated event. After all, the price the customer, you all, pays per lesson is roughly equivalent to the cost of a Metropolitan Opera ticket." And he means it. And so I could tell you about it, but I'd rather show it to you. How many of you out there in TV land have had Archie 211? Okay, most of you have had Archie 211. If you took it with Ed, you were probably treated to one of his songs. Not only does he paint and sing and dance, he writes songs that go with the material that he's teaching. He is the only person in the world who's ever written a song on virtual work, but this is a song that hopefully you all will enjoy. You can even sing along. Yeah. And as long as the technology still works, I'll give you a taste of Ed rather than talking any more about Ed.
10,000 views. What? Everybody together. Here's the cross production. We got pins and rollers. We got members in tension. There's too many to mention. We got cuts of section and of joint. Non-concurrent forces will cause in at some point. Some together. All forces. FPD.
Don't you wish you could sing your way through all of your ARC-E classes? Without further ado, give it up for Ed Saliklis.
Wow, thank you, boss. Thank you so much. That was great. I'm super excited that you were able to do that. Thank you, Emily, and thank you, Cesar, and Brian, I think, is also on the committee, right? Thank you all for the wonderful work that you are doing, and thank you for inviting me to this prestigious talk here. It's an honor and a privilege, and thank you for my neighbors showing up and everything, so this is super cool. In the process of preparing a talk like this, I definitely wanted, a lot of people to show up at the to a talk like this, but I recognize almost nobody knows anything about graphic statics. And I don't mean just on this campus, I mean around the world. Very, very few people know what the topic is. And I thought it would be really helpful for me to break up the talk into 4 pieces. And I'm not going to teach you too much about graphic statics. A little bit, I think, is appropriate, but not too much, because it's a lecture. And at some point, I'll explain this super cool diagram here. This shows up as our theme for the transitions. So what I'll do is I'll begin with the historical background, and I think the historical background actually is really fascinating. Scale Factor calls me a poser historian, as my students in the history class know. But it is fascinating, and the more you dig, the deeper you find layers that were not previously seen, and you can get lost in these rabbit holes. But I'll give you something to kind of tell you that, first of all, I didn't invent this. And second, it's been studied for a very, very long time, and the people who studied it did a really interesting work over the centuries. And then I want to talk about my own story. How did I get involved in this process? Some of the people that I merged with and I consulted with over the years. People often ask how long it took, so that's one of the frequently asked questions. That's the last thing. And then I'll get into the book itself, kind of a description of graphic statics, a little bit of what motivated me to choose the topics, a whirlwind tour through that. And then I put together commonly asked questions and commonly asked critiques. So the last part of the talk is me answering some questions that people have asked over the years. But during that time, I'd like you to think about questions. So all the architects have their Moleskine notebooks, I see, and the Archies have some green graph paper. You could use your phone or whatever, but periodically you should write something down. First of all, it keeps you awake. And second, I may have answered it in the frequently asked questions part. And if not, then we will have a brief discussion at the end. So the whole talk is about 40, 45 minutes. I know everybody's asking, how long is it going to be? So it'll be about 45 minutes, and then we'll have some time to talk, 40 minutes or so. Okay, so we begin with this picture. And Robert Hooke, 1671. So we're in the 17th century. Most people in the room, if you're an engineering student, will recognize Hooke from Hooke's Law. But he uses Young's modulus in Hooke's Law, so that's another whole long story that we won't get into. But Hooke was a fascinating person and a very mysterious, and some people say he was a real jerk to his colleagues, but he certainly didn't trust his colleagues. So the insights that he had were cryptically written in notebooks, on the margins of notebooks. So those Moleskine notebooks that you're writing in right now, those will be collected by your biographers. So take it carefully, collect the notebooks. And here is what Robert Hooke wrote. The true mathematical and mechanical form of all manner of arches for building, with the true abutment necessary to each of them. A problem which no architectonic writer, I think Doug is an architectonic writer. I don't really know what an architectonic writer is, but no architectonic writer hath ever yet attempted, much less performed. And here's the answer. A, B, C, 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 D, D, E, 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 right? And this is what he wrote in the notebook. Robert Hooke's manservant found the notebook. And incidentally, I want to have a manservant, right? This is really cool. If you have a manservant to take care of your notebooks, this is really, you've made it. So the manservant found the notebook, and the manservant was good. He figured it out. Has anybody figured this one out yet? Raise your hand or shout it out if you figured it out already. The answer is ut pendit continuum flexile sic stabit contiguum rigidum inversum. So I don't know how many of you went to Catholic school and studied Latin, but I think you could put it together, right? As hangs the flexible chain, so stands the rigid arch, but inversed. And Hooke was so protective of this idea, he couldn't patent it. So he hid it in this margin of this notebook. Now, why is this so profound? Why is graphic statics so good? Well, a chain hanging like this, it's called a catenary if it's under its own weight, or it's a funicular if it's under any arbitrary weight. That chain cannot be compressed. It can only be stretched. It's only in tension. Consequently, there's no bending in a chain that's hanging. It's impossible to bend. If you flip over a funicular shape like that, and that's called a funicular, it's a catenary if it's under its own weight, but a funicular is a little more general. If you flip it over, the arch has no bending. And bending is terrible. I mean, we always fear bending as engineers because it's a very inefficient way of carrying loads. And in horizontal structures, you can't avoid it. You have to have bending, hence all of the problems that we have with beam design and things like that. But if you could magically create a curved surface without bending, you would have a structure that is really super efficient. About 70 years after the notebooks were written, Polanyi used this idea in his analysis. He was hired to study the cracks in St. Peter's Dome, designed by Michelangelo. And Polanyi used this technique, and you could see what he's doing here. He's hanging a couple of different chains for slightly different loads, perhaps for wind loads, perhaps for statuary, other things, And if the chain lies within the vault itself, within that envelope of possibilities, then there's no bending. If the chain extrudes from the arch in one spot, you would have some tension. It's not fatal, nobody's going to die. If it extrudes in two spots, you have more cracking, nobody's going to die. Eventually, though, everybody will die because you will start to have too many cracks and the vault becomes a machine, a mechanism, and it's unstable and it will collapse. So that idea, and this is a crazy part of the story, so that idea was taken by, who is this on the left? Does anybody can take a guess? Robert Hooke's era. That idea was taken by Christopher Wren. Christopher Wren and Robert Hooke were business partners. After the Great Fire of London, there was huge work in infrastructure renovation. So these guys were business partners. They were making money. And Hooke whispered into Wren's ear, hey, I heard you're building a church. It's called St. Paul's, right? Yeah. Why don't you use this chain mechanism? So it's like a secret. The chain is within the two vaults of St. Paul's. It's not one vault or the other. It's buried in there. That's in the 17th century. But if you're a real historian, you just keep going backwards further and further, all the way back to 1586, and Varignon used this technique. And I love these pictures by Varignon here. On the left, we have somebody holding up a rope, and we have four forces. Gravity is down, so those forces are vertical forces, and they're pulling the chain down, and the chain is straight between the forces. I think it's intuitive. Somebody nod. It kind of makes physical sense. Thank you for that nod, Rob. So, but now Varignon takes it one step further, and I love the little hands, like all the little hands here, right? They're all pulling, and they're pulling, do you notice they're pulling at different directions here, right? So they're not just pulling down. I think many archies in the room and many architecture students in the room would have trouble solving the statics of the picture on the right. It's not a trivial problem to solve algebraically. And it was solved closed form exactly by Varignon in 1586. One of the things that drives me crazy whenever I talk about graphic statics with other engineering professors is they say, well, I do graphic statics, you know, I show some of the forces as a bunch of vectors adding up. So what do they mean by that? They say, well, there's a force here, and that's this guy's hand, letter K, and I'm showing it as a red arrow because Al knows that forces are red in nature. And we draw it to a different scale. This is important here. The scale of the force diagram that I'm going to sketch up here has to be comfortable to fit on a page. This might be 100,000 pounds or 750,000 pounds in a structural engineering application over a 30 or 40 foot span or whatever it is. So you draw the form to some scale, and you draw the forces to another scale that is independent of the first scale. They have nothing to do with each other. So you draw a diagram of your form, and on the same page you draw a diagram of the forces. The forces now, I think everybody in the room knows what's happening here. You do this in physics, right? Head to tail, head to tail. This is vector addition. And at the end, there's an equilibrating force. And what is the equilibrating force going to do here? It's going to go up or down. The equilibrating force, this is the easy part. Up, yes, it's going to go up, right? And we're showing it as a dashed line. This is not graphic statics. This is simply vector addition. There's something else in this picture. Not these guys with the hands, but this thing here. This is called the force diagram. So this is the form diagram. This is the thing that we're designing and the thing that we're analyzing. And I'm going to talk about that a little bit. This is a design tool and an analysis tool simultaneously. And this is the force diagram. But there's something else in the force diagram that nobody noticed yet, and that's these lines here. These lines here correspond to the shape of the form. So the blue lines here on the force diagram are linked to the form diagram through the funicular. This thing is called the pole, this spot from which these rays emanate. And the pole is arbitrary. You could drop it down anywhere you want, and you create the force diagram. If you move the pole, you can get larger forces and a smaller sag in the cable. So the form diagram and the force diagram are linked, and they are reciprocals of each other. So this idea is super profound, this idea of reciprocal geometry and projective geometry. So in the 19th century, mathematicians studied projective geometry. In the 19th century, civil engineers studied projective geometry. Projective geometry, that thing that art students study now. How might something in 3D be projected on horizontal planes off to the side or vertical planes? So this idea of depth of field, perspective, all of that, that was studied by mathematicians, and civil engineers could do projective geometry in their head. One of the major authors of projective geometry was Luigi Cremona in 1888, and Cremona wrote a book on projective geometry, and he was using these graphical tools to solve calculus, to solve differential equations. And then at the end of his first book, there's like 20 pages, and it says, oh, by the way, this could be used for static equilibrium in physics also, and he gives a couple of examples. So in the beginning of the 19th century, people used to call these Cremona diagrams. At the end of the 19th century, the beginning of the 20th century, they used to call them Cremona diagrams. So sometimes old-timers will still talk like that. They'll call it Cremona diagrams. So is this new? Well, there's nothing new under the sun, really. Gothic masons knew these secrets, not as graphic statics with rigorous analytical tools, but with a study of voisures. How much does this block weigh, this beveled block that's cut? That's W3, and there's W3. How much does this voisure weigh? That's W4. It's coming down. And the Masons Guild, that secretive Masons Guild, which we still have even in San Luis Obispo, we have a Masons Lodge downtown, they had it in their notebooks about the link between form and forces. They didn't have this, though. This is the force diagram with that arbitrary pole, but I put that in here so that you see the parallel lines of the force diagram linked to the form diagram. So one of the weird things about this, when I study this, my head is exploding, because I went, as Al said, I went to, pretty big name schools, right? Nobody ever mentioned this to me in the history of my life. And when I look at it, it's so profound when I realize people have studied this for centuries. Every civil engineer on the planet knew this material in the early 20th century. This was part of a civil engineer's and an architect's training. What happened? Well, we'll try to unpack that in the fourth part of the lesson. So in 1888, we have Professor Carl Coleman really codifying this with his classic book, which is really out of print. I don't have this one, Grafikstatik. And Ritter was the professor or a colleague of the chief designer of the Eiffel Tower. My Arc East 260 students, who was the chief designer of the Eiffel Tower? Maurice Koechlin. Let's give Sarah a round of applause there. Very nice. So Ritter worked with Koechlin on graphic statics. The Eiffel Tower was designed and analyzed exclusively by graphic statics. We do it in a simple way in Arc E 260. Ritter was a colleague of Koechlin. Coleman was a colleague of Koechlin. Coleman was Ritter's professor at ETH Zurich, the finest architectural engineering school on the planet, despite what my boss says here. It's ETH Zurich. And Ritter was Robert Mayar's professor. So Robert Mayar, who we know from our history class, Salgina-Tobel Bridge was a masterpiece of graphic statics. Coleman was Mayar's grandfather in some sense here. But look at what Coleman is saying. Okay, ladies and gentlemen, if you order today with graphic statics, you can get equilibrium, no problem. You can get the centroid of forces, no problem. I didn't even talk about it, but it's in the book. You line up the trajectories of the beginning of the form and the end of the form, where they intersect, that's the centroid of all your loads. It's easy peasy, super easy. And it makes a ton of sense because those are axial forces. Everything boils down to an equilibrium of a point. But Coleman is saying if you order today, before 6 o'clock, I will throw in something. And everybody in the room should, well, not everybody, but most people in the room should be able to answer. What is he going to throw in at no extra cost for a beam subjected to lateral loads? What does this look like, ladies and gentlemen? That thing under the beam. The bending moment diagram. So you get the bending moment diagram for no extra charge. How do you get the bending moment diagram? This is crazy. Watch what happens. You make a funicular, you just put a pole down, it doesn't matter where you put the pole, and the funicular starts at the pin. You really have to start at the pin because there's two unknowns there. And you draw the funicular, and it ends where it ends. It ends where it ends. And then you draw a line back to the funicular. That's called the closing line, this dashed line here. The vertical distance from the funicular to the closing line multiplied by the horizontal span of your forces. This is a force diagram. This force times this distance is the bending moment at any cut. It's super, super cool. And it works exactly. So how can this possibly work? I'll just breeze through this really quick here. So you drop down loads from A to B to some comfortable diagram. You put the pole wherever you want. This is the closing line. And you can make the pole anything you want. The closing line ends where it ends. It's that distance multiplied by this, and I call it H force, a horizontal force. It's actually the horizontal force in the cable. If this was a physical cable, it would be the horizontal thrust, which is going outwards for us in that problem there. The highlight, the zenith, the best moments of graphic statics lives happened in 1921. And people ask me, who's your competitor for the book? This is my competitor, and he kicks my butt. This book is amazing. I mean, it's totally amazing. You can get it as a PDF for free. I don't recommend that, though, because there's plenty of copies for like $7. You could still get this book by William Wolfe. Our dean has this book on her bookshelf. This is an important book. It's literally amazing. The stuff that he does in here is overwhelmingly beautiful, incredibly detailed, richly complicated. Here he's analyzing an enormous truss frame object, and he's designing it simultaneously. You get every force in every member, and you could redesign everything. I can redesign everything by sliding a mouse, but he would have to redraw these pictures. But the geometry was not overwhelming for these people who knew projective geometry. I want to give a little shout out to architectural engineering here. He was a professor at my alma mater, University of Illinois. And I channel this guy. You know, Scale Factor can attest to me dropping some F-bombs at the dining room table while I was writing the book. But I'm channeling Wolfe. Like, I really got into his head. I think he was whispering in my ear. Just want to talk a little bit about this picture one more time. This is a crazy example, and I recreated it in the book, but I gave him total credit for it. It's a truss. It's got gravity loads, and it's got wind on one side of the load, but it's an indeterminate truss. There's a pin at the left and a pin at the right. And what Wolfe is doing, he's saying, how can I shape the truss for this load such that the horizontal component is the same on either side so that I can simplify my connection design? And he goes through three trials in here. And this is so deep, I can't overstate what's happening here, because this is the link to the Airy stress function, which I've talked about with the graduate students a few times. There's a direct link between these shapes and the Airy stress function, which is a super high-end theoretical kind of, but practical construct. Okay, so that's the historical background. I'll speed it up a little bit. My own story. How did I get involved with all this? It really does begin in the modern era with Wacław Zalewski, a brilliant Polish engineer, and then he became an educator at MIT. Zalewski died, but he lived a good long life. I think he hit 100. I spoke to him on the phone a few times, and he was totally blind for many, many years at the end of his life. But he wrote these books, being blind. And I asked him, I said, how could you have such powers of concentration? And he says, when I was a young boy, I fled the Nazis, and I hid in the forest. And I learned to concentrate when I was hiding under a tree in a forest. This is what he told me. And he was an engineer, and this is a grocery store. It's called the Super Sam grocery store. It's a gigantic grocery store in Poland, and he's using graphic statics to design and to analyze these magnificent structures. So Zalewski meets Ed Allen, and most of the architects in the room know Ed Allen. You've used the Architect Studio Companion, the big fat book. He's written a whole bunch of books. So Ed Allen partners with Václav Zalewski on the first book, and it's called Shaping Structures. And that word is really nice. That title is really nice because this is a design tool. This is not primarily an analysis tool. This is really a design tool. What shape should I have for my building such that I can control the forces, even if it's statically indeterminate? So they came up with this book. I must admit, I was given this book. You know, professors get books, and I opened it up. I'm like, what the heck is this? Like, I had no idea what was going on. I didn't learn the material. I kind of put it aside. And a lot of other people did the exact same thing. So the sales were really pretty bad on Shaping Structures. And then they reinvented the book, and they called it Form and Forces. They chose the Super Sam grocery store as the title. And this book really set the spark for the revolution. And the revolution happened all around the world, but it really started at MIT. And it starts with this man over here, John Oxendorf. So John was not Ed Allen's student, but they were colleagues. John worked with Jacques Heyman, who studied, one of his famous books is The Stone Skeleton, Heymann. We have it in our library. He's analyzing how are cathedrals made? Where's the thrust line in a material that has no tensile properties? So, and John became enamored with thrust in masonry structures, and he became an expert on Guastavino, and he came up with this book, which my students know from the history class. We talk a lot about Guastavino. Philippe Bloch was John's PhD student at MIT. Philippe Bloch is a certified genius. I mean, John is a genius, right? He got a MacArthur Award. He was here in this room here. So John has been here. He got a MacArthur, the Genius Award. But Philippe is a real genius. You know, so Philippe was John's student at MIT. And Philippe codified the idea of a thrust network analysis. So it's a 3D graphical statics. But it's primarily the idea of shaping a vault. And that became Rhino Vault, that plugin that we use sometimes today in Rhino Vault. And then Masoud Akbarzadeh was Philippe's student at ETH Zurich. So he got his PhD at ETH Zurich. And Philippe recognized something that really nobody else recognized. And this is kind of hard, but I'll show you a picture. The force diagram is a polygon in 2D. You just go around and you come back to where you start. In 3D, it's a polyhedra. So it's a three-dimensional equilibrium state. If the polyhedra is closed, it's in global equilibrium. And that couldn't be done really easily by hand, yet Maxwell, the physicist Maxwell, who electricity and physics and electromagnetism, wrote one paragraph with 3 sentences in it, and he saw that the forces in 3D form a closed polyhedron. He said, we can't draw it, but we know that it exists. And people have been unpacking that now for, I want to say 5 or 6 years since, well, he got his PhD in 2016, so just a couple years. So this is really new. Bill Baker, the chief designer of the Burj Khalifa, finds out, he was, you could see his name, I think, right there, William Baker, S-O-M. He was on the advisory committee, so he goes out to Zurich, you know, because he knows what's happening. And Bill Baker gets excited about Maxwell's theorem, so he's writing a book about Maxwell. He's getting excited about Airy stress function all the time while he's designing the world's tallest building, the Burj Khalifa. And he's using Airy stress functions. He actually used it to design sports stadia in China right now. So I write an email to Bill Baker, and my students know this story. And in the subject, heading, I write Myron, just one word, Myron. And he's like, okay, he picks up the phone and he calls me. And of course, we're talking about Myron Goldsmith. So that's a whole other lecture, which I've given in public in multiple languages. But we will not talk about Myron. So I get to meet Bill Baker. And I got my interview questions, and I'm going to interview him about Myron. And I go to his office in Chicago, and what's on the desk? And I'm like, okay, William Wolfe is whispering in my ear, right? And on the wall, these are all Mitchell trusses here, which is a graphic statics tool. So I said, Bill, are you into graphic statics? And he was just learning it at this point. So here's a graphic statics of a simple truss. My students will recognize Broadgate Exchange House back there, which was not designed by graphic statics. He said if they would have known graphic statics, it would have been a lot easier to design that building. So, and then something else happened, and I think it's really important to shift gears just slightly. John Oxendorf's student who didn't show up on this picture is Michael Ramage. Michael Ramage and John Oxendorf designed and constructed the Mapungubwe Interpretive Center in South Africa. And what they did was they used earthen tiles that were made by these workers. And they made thousands and thousands of these tiles, which are not really good material. So they're using crappy material, and it's a labor-intensive process, but they're paying a living wage to a dozen men who fed their families for a year and a half during this project. So there's a huge social critique here that is very important. The scientific critique is the graphic statics. The social critique is, can we use the world's worst material in a highly efficient way and pay people living wages to make it? Not a robot 3D printing it, but people building this. And there's a lot of fun stories about this, about the work ethic of South Africans, what it means to work hard. They quickly became experts. This is a Catalan vaulting, which is what Guastavino used, and that's John's influence. It's a quick-setting mortar with no scaffolding. So you don't need any scaffolding when you're making a funicular Catalan vault, because the weight of this tile is held in place by this quick-setting plaster mortar. And you may say, well, wait a minute, I see formwork. And that's not formwork. These are three-dimensional guidelines to build the building. They're just three-dimensional curves in space that are telling the workers where to put the tiles. And this is the first building in the modern era to be designed with graphic statics, but it's 2D slice form. So the architects in the room know what I'm talking about when I talk about slice form. Taking sections and looking at slices, and again, envelopes, no seismic. It's at the northern edge of South Africa, wind loading. So they're getting an envelope of thicknesses. And then they did a seismic test just to learn, and this was really cool the way they did it. They said, we can do graphic statics for those vertical loads, those weights that are just hanging. And then they said, well, what if we lifted up the shell and the shell is sideways, but it's only subjected to gravity? Now the gravity is going down, but the shell is tilted. So there's a vertical component if you flip it back and a lateral component. So they did that. They tilted the shell on paper to do the graphic statics, the force diagrams right here, and they came up with a spectacular structure. So at this point, I'm completely besotted by graphic statics. And a 15-year journey or so begins. You know, Tom DeSanto always says, how long did it take? He gets that question, how long did it take you to make that painting? And he always says 15 years. And I use the same answer. You know, it's not like a year's worth of work. It's a little bit of background that made me able to do this, right? And I have maybe the world's greatest collection of graphic statics books in the world because there's very few people interested in these books. And I bought them for like $7, you know? And they're gone now. There's hardly any. Like this one is gone. I have the only copy of that book. I have one in my office right now. There's 2 copies of the book, and I got it from Columbia. There's only 2 copies left in the whole world. But this is super cool. I actually got the first edition of Cremona from 1888, the one where there's that little chapter in the back. Oh, yeah, by the way, you could use this for physics, right? And then I got the 2nd edition and the 3rd edition. And I've showed this to book collectors, and they're stunned. Like, they're like, That's your life insurance policy right there. But I don't think that's true, but it's kind of amazing. So you can come into my office and touch these books, but I won't let you use them. So, but and there's Wolf right there. So the reason why I got the orange book, by the way, is he did a little bit of 3D stuff, and this is from the 60s. He was in India and Bangladesh specifically, in that area. It's crazy. So the plunge into shells. So I wanted to be John Oxendorf, and I wanted to make a Guastavino, and Robert knows that he suffered with my hyperbolic paraboloids for a while during that mania of, I just want to be John when I grow up, right? And I forced a couple people to do this. So one of them was the plunge into 3D shells. Ansgar Killing, Dankeschön, and Claire Olson is over here. Let's give Claire a round of applause there, and Ansgar. Thank you for being patient with me. I just said, let's just go into it. We got to do the shells. And we started really slowly. The latest version, if we have alumni of the course, I think, in here, the latest version is pretty dialed in with kangaroo and grasshopper and everything. It didn't start that way. We started with slice forms. We started with the tripod that Masoud Akbarzadeh is doing with the three-dimensional polyhedron, and I was explaining these polyhedron to everybody. And it was a little clunky, but it all works. And I'm crazy about oculi. I just love the oculus. The shells are very forgiving of holes. I use the analogy of just pouring water on the shell, and it'll flow right around the hole, right around. A little bit of tension where the water separates, and then compression again. So we have some spectacular things. We do this in 10 weeks, 3 weeks of design. So they're done in 3 weeks. Then 3 weeks of analysis, and we do buckling, we do seismic, we subject it to Northridge, to IBC, and then 3 weeks of construction planning, and then we actually build it. So different sites. Claire and Ansgar always pick the sites. I love it. And most of the structures then are breathtaking at the end, regardless of how we did it. So this is one of the earlier ones. This is one of the later ones, and the classic sort of picture of archi or and architecture students sitting on their shells that you've seen in the history books of the college. We try to recreate that. We celebrate it with some California grape juice here under the moonlit sky. And then one of the student groups really did an homage, and again, this is Claire's idea, an homage to Candela, and with perforations. And if you know our Uncle George was the editor of Arts and Architecture magazine, and on the cover of Arts and Architecture magazine was a Candela warehouse that had such perforations. And then, shout out to Vince. I don't know if Vince is here. In the last studio, I said, these guys were really good. And I said, I love the sketches, the pen and ink, the watercolor. Could you show us how this becomes like a shell, through Carumba? And Vince says, yeah, I could do that. So let's see if we could do it, Vince. Come on. Hopefully we'll get a low respectful whistle out of this if this works. Right? B+ work, right? And then a Sugimoto photo here. So these are still out there. We're going to tear them down next week. So go take a look at them. Super fun. Okay, so the book itself, I'll breeze through this pretty quick here. It was published by Springer International, prestigious international publisher. Who's the audience? I think you are the audience, and I mean everybody in the room. If you're an architecture student, an archi student, a high school student, or a retired person who just wants to do something other than Sudoku puzzles, you could do this, right? I think you could do graphic statics to just stay sane, right? Everything that Wolf does, and then I added the shells, but I don't do anything as deep as Wolf did in 1921. So obviously 2D determinate, everything is in there. 2D, indeterminate, everything is in there. Frames and shells, points in space, and everything is done. I drew every picture with GeoGebra, which is a kid's program. So this is a children's program to teach them geometry and algebra. It's a free program. You could put it on your phone. I use it on the airplane on my phone, and I talk to the people sitting next to me about graphic static. And then they ring the bell. Can we change seats? But the people who design GeoGebra are geniuses also. They're all Cambridge mathematicians. There's 3 people. And they made this program that is completely 100% parametric. And I asked them, why did you make this program? And they said, for the real teachers. And I said, who are the real teachers? And they said, the people teaching high school math. That's the most important person right now. We need to get those kids excited about math and mathematical thinking. So every picture that I did is done with GeoGebra. Sales, not so much. I sent this to Scale Factor. The book was published in end of 18, and in January of in January of 19, on January 18th, Friday, January of this year, I sent this to Scale Factor. I'm like, wow, look at this, only 3 copies are left, more on the way. And then right before this Hearst lecture, only 3 copies are left. So I have this image of like an Amazon warehouse and these guys on fork trucks looking at these 3 orange books on the shelf somewhere in the corner getting dusty. And 3 more are on the way. So, but anyway, so it's not, this is another thing that drives me crazy. Well, isn't this the semi-graphical method that we've been doing? No, it's not the semi-graphical method. What this is relating the displacement to the bending moment, but not through this differential equation. This is the classical differential equation. This is not the displacement of the beam. This is the hardest part to understand. The beam, a virtual chain out there takes this shape. The beam does not take this shape. Because this doesn't even end on the support. It just ends wherever it ends, right? So what's going on here? Well, the derivative of the moment is the shear, and the derivative of the shear is the weight. So what this is doing, and this is why Cremona, the mathematician, was doing this. This is a double integration. So this process of drawing these lines is actually a double integration. That's why it is exact. This is an exact method. It's not approximate. And it's so unbelievably easy that you could do it on your phone. You could do it on a napkin, right? It really does work. So real quick video of just how to construct this. It's super fun. You pick a pole, any pole, and you just start drawing lines, and you snap it to where the load intersects. So if it was a Varignon picture with the hands pulling, the trajectory wouldn't be vertical. And you just keep snapping like this. It's actually quite mesmerizing. And you end where you end, and then you draw a closing line. And that's it. That's the whole method. The width of this is h-force. And if you wanted to make an arch, you just flip it over, and it becomes an arch. So it's super, super easy, and it's super intuitive. And then if I pull harder, I have less sag in the cable. But this is not about designing a cable. Let me get into that, what it is and what it is not. So it's an exact method. It's not an approximation. It really shines as a design tool, but of course you can analyze structures with it. The other cool thing about this is that the more complicated the problem is, doesn't add any burden on you as the person running the machine. And the exact opposite is true in algebraic statics. If you have a bunch of problems, a bunch of loads, you're going to screw this up somehow. Like if it's a complicated truss, you're going to screw this up. Complicated truss with lateral loads or a frame. You can't screw this up because it's the exact same technique over and over again. It doesn't make any difference how complicated it is, and the key is the funicular. How do I do the indeterminate stuff? Well, I had Sidney Gallion help me with this project. We added kinematics, which is the deformation of the solids. So you can't solve a statically indeterminate problem only by equations of equilibrium. You have to look at how the thing deforms. So that's what we did for trusses in space. In the book, I also added a chapter on what Guy Nordensson actually coined this term at Princeton, the 2.5 dimension problem. We call this the rigid roof or the flexible diaphragm. It doesn't matter, but it's a roof that's suspended on columns, and it's being hit by lateral loads. It's really a planar problem. If you look down on it, it's a plane, but the height comes into effect when you look at the bracing. I know the bell's ringing, but I didn't start at 5, so I'm just going to keep going a little bit. And then shells, just a little bit more, and then we'll answer questions. So now, just to kind of get you familiar with the idea of slightly more complicated problems that could lend itself to formal ideas. Here's a beam with a cantilever, and the loads, of course, are knocked off by some scale over here. The pole is arbitrary, and I can change this shape, and I can truss up that shape. I can make a Virendale truss out of that if I want, and that's exactly what I'm doing with my seniors right now. And you would maybe use that shape if the Virendale is below the deck, if it was a long span structure, or maybe it's above the deck. We see evidence of that even on our own CM building on the walkway going over between that building and building 21. So it could be a form-finding tool, right? It's not just an analysis tool. And then there's one more lesson in here on why this is such a great learning tool for architecture students. So here's a truss. It's asymmetrically loaded, so these two loads are bigger than that load. And now I want to get these internal bar forces, because this funicular is only for the external equilibrium. What if I want these internal bar forces? Well, I just use the same construction to get these points, and it's completely analogous to method of joints. I would start here, where there's two unknowns. I wouldn't start on the anterior, and I would locate point 1, and I did that by this slope, which is common to A, and this slope, which is common to E. So 1, I cut that through, and then I can move on to point 2, just like I do in algebraic statics. So I would not attack this number first. I'm not finding a joint, I'm finding the number, and once I have the numbers, then the problem is unlocked, because this is a force diagram. So if I draw a picture describing going from from this to this, that would be here, and this is drawn to some scale. That's the magnitude of the force in this element right here. And if I draw an element from here, that's this element here. This is the force in this element. And if the architect says, well, I want a more slender profile, I want a more slender profile for my truss, I don't want that big steep truss, you can say to the architect, that's not a problem whatsoever, because I have GeoGebra, right? So you don't like this tall truss? Fine, let's make it slender. And let's make it slender. What's the force in that element right there? You show this to an architect, and they understand immediately that's the implications of that slenderness. It's graphical, it's intuitive, you get feedback right away. And then for arches, it's super interesting. It goes back to this medieval Gothic idea. Here's a 3-hinged arch. I'm not going to go through the construction of the funicular, but the funicular is the purple line here. You can kind of see it like a string being pulled. I mean, I did it for anti-gravity here. But where the arch strays from the funicular, you're going to have more bending, right? You're going to have more bending. And for an envelope of solutions, you could come up with an extremely efficient structure visually linked to each other. And then Masoud, Philippe's student at ETH, said, well, wait a minute, what else can we do with this? So he's in the 2D world. Let's start with the 1888 funicular and find the centroid of each of these panels. You find the centroid of that, and you start branching off, and you come up with amazing structures. An infinite number of possibilities, all 100% rational. All of these are funicular. None of these have any bending whatsoever. And you'd be hard-pressed to generate so many ideas so rapidly by any other technique. And then Masoud did it in 3D, and this is what we did with the students in the studio. The faces of the polyhedra, the area corresponds to the magnitude of the force. And you could bifurcate or branch as many times as you want, and you could develop a shell shape. I didn't do that with the last studio with Claire in the winter. We used it kind of became a black box. We used Kangaroo and Grasshopper, and one group did use Rhino Vault, the Philippe Bloch tool. But right now what we're doing with the seniors is thinking about using a parabolic or a funicular kind of, and they're hyperbolic paraboloids, but for the purposes of the talk here, just think of this as funicular and that as funicular, just as slice forms, and then you could drop another funicular between these, and you could make spectacular spaces. Or this one, which is a little more complicated, this is in the book, what I have is one funicular going one way and another funicular going another way, and they kiss at the crown. I have a little video just to kind of show you how that just the geometry of it. So they kiss at the crown right there. So there's a funicular, then I made one in the front, and then one in the other, and that took 5 minutes. Like, it's literally super fast, and it's extremely, extremely efficient. Okay, so now the last part, we're almost done. The most common questions and critiques. So I call this frequently and infrequently asked questions. Okay, so the first is obviously the most common one I get. What is graphic statics? And I think I told you, it's a centuries-old tool. It's exact, but it really shines as a design tool. It's a form-finding tool to shape structures. That's why Zalewski and Allen's first book was called Shaping Structure. So I think I got that one done. Why is graphic statics so good, right? Well, I hope I answered some of that. It can solve any problem that we will have in the undergraduate curriculum, and it has implications even in the master's program if you take it into that Airy stress function idea. So I think it's super, super malleable in its applications. You could do this with freshmen. You could do this with freshmen. You could do this in our graduate program. All right, the third question. If graphic statics is so good, why doesn't anybody teach it? That's a good question, and it's a difficult one to answer. Graphic statics was the thing universally in the beginning of the 20th century, and it disappears. Like by 1950, 1960, it's gone. And it's gone. And what is rising in the engineer's toolkit around the 1950s and 1960s? The calculator, and then eventually the finite element method. So the finite element method begins in the aerospace industry, and it works its way into civil engineering really quickly through a lot of California professors, by the way. And I think our whole profession just became enamored with finite element methods and this huge, huge computational power that just kept growing and growing and growing. Simultaneously, we're losing our ability to draw, we're losing our ability to sketch, we're losing our ability to watercolor, right? And we're losing our ability to think algorithmically. And that sounds like a paradox, but I teach computer programming within an engineering discipline. And I could see some people can think computationally and others cannot. It's a very difficult skill to teach. This requires computational thinking. If you are doing this yourself, you have to think about setting up the script, right? Setting it up, making it look good, making it efficient. But I think the culprit really is the computer. This finite element, which is the ugliest possible way of solving any engineering problem. We have so many beautiful methods, and they're almost all gone. We've tossed out methods that when I started here, we no longer teach at Cal Poly. All right, this one was great. An old guy, a really old guy, Wolfgang Schuler, who wrote a lot of books, he hates graphic statics, and he says, why isn't that? It's a 19th century tool. And the answer is yes, it is a 19th century tool, which is completely relevant in the 21st century. The fact that Bill Baker and Philippe Bloch and John Oxendorf and Masoud Akbarzadeh are studying this, and I didn't even mention everybody else, there's a whole bunch of people really studying this and getting enormous findings and enormous mysteries. Maxwell's theorem is still not unpacked. That three-sentence thing that Maxwell wrote is still today in 2019, still not unpacked. The last one. If graphic statics is so good, and if it's a 21st century tool, and if we teach it, can it change the world? Now, this is definitely an infrequently asked question. And I'm going to close with this one. I think, I'm a little dramatic, right? But I honestly think that we could change the world with this in a very specific manner. And here's what I mean. The fact that we could get this free program on our phone, we don't even have to have a laptop, right? And the fact that it's so visual and intuitive, and it's so beautiful. I mean, these drawings are really aesthetically pleasing. Your homework looks like art at the end of this, right? We could get kids excited about buildings, architecture and engineering. And I mean high school kids all over the world. The whole book, there's no units in my book. So there's no pounds, there's no newtons, there's no inches, there's no feet. It's force and length. Force diagram, form diagram. And I think we should be doing that. I think we should be showing kids, why are kids learning physics and chemistry in high school and not graphic statics, right? So I think they should be, right? They should be. And I think we could really change the world. We could empower a lot of people because it's very, very simple tools. Plus, it is hyper efficient at the end of the day. And I come back, I'm interested in designing concrete shells with the world's worst concrete. I want the world's worst concrete. I want stuff that just breaks in tension, like a chocolate bar, right? Like a frozen chocolate bar. That's what I want to build out because in compression, it's fine. And that requires a designer's imagination. So there's so many lessons here that I think are revolutionary. But now I'm done, and I would like to hear your questions. I thank you for listening. So we'll just take a few minutes. If you have to leave, you could leave. But it's actually kind of a dynamic time when we do have some question and answers. So I really wanted to get through it in a timely manner. General questions, specific questions. Yes? Okay. Thank you. I think I haven't done that at all. I think the only answer that I could have is that when using masonry or earthen tiles, they're very, very good from an economic point of view because it's cheap, but they're also very good thermal barriers. So I'm not at all interested in carbon fiber, reinforced materials to solve third world problems. I think people can build third world, and I don't mean that in a derogatory way, but less affluent nations can use this technique because it's a labor-intensive technique too. So there's a social part to it, but they could last forever, I think, too. So there's another sustainability aspect. But generally, it's still a physics-based engine, but it's a different way of kind of thinking about design. Like, I'm going to make super low-tech construction with super high-tech design thinking. That's what I'm interested in. Yes? Yep. I know exactly what you mean. I don't have the app. I want to do the app for the senior citizens, actually. I think that would be super cool. I don't have an app. MIT came up with a few, but I think the problem with it is that it becomes a black box really quickly. And literally, I could teach you this in 25 minutes. If we sit down together, I could teach you the whole book in 25 minutes. And literally on a napkin. We could sit down and do it on a napkin. And the beauty of the algorithmic thinking or the computational thinking arises when you start writing your own scripts. I got some students trying to do this in Grasshopper, and they're doing it, but it's super clunky. I mean, GeoGebra is the way to go. It's so sweet. It's so easy. I mean, But we're doing it in Grasshopper too. So, and then I was joking, I just realized in the latest Kangaroo there's a catenary button. Like there's a button that says catenary and you push it and you get it. And it's like, that's why my sales are so crappy. So it's like... Yes, John. Yeah. Okay. I think I know what you mean by attractor points and things like that with Rhino when you're pulling. Okay. We actually had one studio, and I think Claire will remember this one studio, where we actually did students where they're just morphing shells. And you could do that. You can get pretty close. You actually do get pretty close. I mean, Rhino right now will let you pull stuff in 3D space, but it's just pulling, you know, there's no reason for pulling it one way or the other. Your eye tells you where it should go because your eye sort of knows where it should go, but it's a different process. So this process is really using a different skill set than simply pulling. You know, Heinz Eisler did this with cloth in the 60s, but they all look like hanging cloths, right, at the end of the day. Ours out there, they don't look like hanging cloths at all, right? They're completely different. Gaudí did this with chains, but that doesn't look like hanging cloth. But it's a centuries-old technique, but a highly disciplined tool, highly disciplined. Yes? Yeah, I think that's always the hope, but there's one piece missing. You have to develop their intuitive skills. So that takes practice, that takes precedence, that they have a database of things that work, right? And I teach the third-year studio right now where they are not comfortable with their structural intuition, and I'm saying you have a lot of structural intuition. But they're 40 weeks into structural engineering. I would not trust a child's structural intuition, but I would trust a child's output from GeoGebra. And then over time, that intuition, I think, will develop. It's like a code of ethics, right? You could say, I have a code of ethics. Well, what went into your code of ethics, right? It's a lot of layers went into it to build it up. But yeah, that's the goal, right? We want to merge left brain and right brain thinking, if that's a thing. The discipline and play, for sure. That's super important. Okay? Are we good? Yeah, one more. Yeah. Yes. Uh-huh. Uh-huh. Good. Absolutely. Absolutely. Yep. Right. Right. Mm-hmm. Mm-hmm. Waste. Yeah. 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 Absolutely. Yeah, it's a completely valid social critique, and he's my neighbor, but I didn't plant this question. So it's a fantastic question because graphic statics died in the 50s and 60s. Thin-shelled construction dies in the 50s and 60s too, due to the bad guy Eero Saarinen, as we know from our history class. But it's also linked to the rise of union labor. And I'm pro-union, I'm in a union, right? But that idea of hiring a carpenter to make 3D formwork killed shell construction, coupled with the fact that engineers don't learn about shells. Nobody learns about shells. Even at the graduate level, it's not very common. So the answer is yes, we have been thinking about that. I tried to get a patent on one idea, but I haven't really done it yet with earthen formwork. So we've experimented here at Cal Poly with earthen formwork. Like, what's easier than that? Like, you got earth, let's just make a mound that's shaped to the funicular shape through computer-controlled guides, like they did in Mapungubwe. And we also use the inflatable, which is super cool. Dr. Dante Bini of Italy made about 1,000 structures out of an inflatable. We've done a couple here at Cal Poly, buying 5mm painter's tarps at Home Depot and ironing them together and running 25 pounds per square inch of house air and inflating it, and it works. And that's really sweet. So I think the answer is yes. I'm very much in favor of super low-tech construction with very, very humble materials, coupled to this hyper-rational design. I don't want it to look like a stick hut, you know, that we would have had 2,000 years ago. I want it to look high-tech and polished. I think shells is a perfect culmination or a perfect meeting point of the architecture and the engineer and the construction disciplines, because to even understand shells at all, you have to really have your foot in all three camps, I think. Yes? Yeah, I love that question. I put the shells on there because that really was a very personal motivator for me. It's screamingly tempting to make a shell for me, but just to set the story straight, this technique also works on beams and trusses and frames and points in space on the rigid roof. So the technique can be used on all those structures. So shells lend themselves to long span instead of high rise, right? So they're very, very efficient on long spans. But what I welcome your help if you want to help me on this. I haven't had anybody do it, but I want to do like a series of funiculars like hanging off of each other, right? So you got one chain, and then you got another chain below that, and it's funicular, and then a third chain below that. That's got to work, right? I mean, that has to work, but nobody's done that, so maybe it won't work. I don't know. But it's super cool, right? It's a super cool idea, and I would love to see it. But constructability becomes a nightmare. Like, you'd have to probably cure the first shell, and then not put earth on the second one, but maybe an inflatable maybe then. So that'd be super fun. Let's do it. Yes? Absolutely, absolutely, absolutely. And Philippe, you know, the guy in ETH, he's doing floors with this, but on a micro scale. So you could find him on YouTube. So he's got traditional concrete slabs that have funicular ribs within the slab, and he's reducing the weight of the concrete slab extraordinary amount, 50%, something like that, on a slab, which is the worst possible shape, right? A flat plate subjected to vertical loads. That's going to bend like crazy. But he's got small funiculars built in there. Those are laid with a robot, you know, with a cementitious paste, a robotic machine laying that down. For walls, undulating walls for sure, but if it's a straight vertical wall, the load flow is it's vertical, so you could perforate it, but we don't do that. Lateral, yeah, for sure, then the curve shape, the hydrostatic pressure kind of thing, yeah, like a thin arch dam, for instance, is a perfect example. That can be designed, yeah. Good? All right, thank you very much. Thanks for attending.